Okay, so equivalence relations, and hand in hand with equivalence relations is the notion of a partition. Okay, equivalence relations and partitions. This is just going to be an extremely simple picture. It is a set with lots of elements. Okay, so it's extremely basic. But one of the operations we're going to do is we're going to take a big, complicated set and we're going to split it up into smaller sets. Split it up into a collection of subsets. And you do this in a way that's unambiguous. Okay? You split it up into a selection of subsets. There's no overlap between the subsets. Each element is in one and only one of the subsets. Okay? So this is a large set partitioned into non-empty disjoint subsets. Partitions. That's what a partition is. A partition of a set is where you split it up. You split it up carefully and exactly. You got a bunch, maybe an infinite number of subsets, maybe. But there's no overlap between the different subsets, and every element of the original set is in one of the subsets. There's no sets left out. We use that word about countries. You can remember that principle. It connects with the idea of partitioning countries. Right, history, different countries join together to form bigger states from time to time. From time to time, big states get split apart to form smaller ones. Okay, so India was partitioned into India and Pakistan as it gained independence from the empire. Ireland was partitioned, Northern Ireland, Southern Ireland. Right. So if you're splitting a country up, you certainly, if you want to split a country up, you certainly don't want to have any overlap, because an overlap is a disputed region. But two more than one country claims, so that you can't have the wars or whatever. Okay? So a partition of countries certainly should have no overlap, and it should certainly not leave any part of the original country unassigned. Yeah, if you partition a country, you don't want to leave a small piece of land that's just okay. That's just not a country. Well, if there's people living there, then they're stateless. So this idea of not overlapping and each of them being non-empty and leaving no gaps is, you can kind of see that in the way that partition is used in international relations and politics as well. Now, an equivalence relation, a partition induces a relation amongst the elements. So the elements of the original set, all these elements here are related to one another. They're all in the same cell, they're all in the same subset. All these ones over here are related to one another. And this relation is called actually an equivalence relation. And there are three key properties that an equivalence relation has. Now, when he talks about it in the book, we very often use this tilde character on the keyboard. Let's move around different versions of keyboards. We'll put the hash key on this one. Tilde system. So you should think of tilde as being like an abstract representation of a relation like equals or greater than or contains or is an element of. It's a mathematical symbol that when you put it between two objects, it forms a statement. Something that might be true or false. So if we call this large set X, for every element little x in the set, X is related to X. X is related to itself. Well, that's kind of true, because every element is in the same subset with itself. That's kind of This is called that's called reflexivity. The relation kind of reflects back, so everything is related to itself. The second property is symmetry. For all pairs of elements x and y in the original big set, if x is related to y, that implies that y is related to x. Now remember, we're talking about the relation induced by this thing. So this is the relationship of being in the same subset. So if x is in the same subset as y, obviously that's the same thing as saying y is in the same subset as x. So this relation x tilde y, x is equivalent to y, means now for any pair of elements, it may or not be true. Like for this x and this y, they are related to each other. They're both in the same subset. But this x and this y are not related to each other. So x does not tilde y here when I'm talking about that x and y. When I'm talking about that x and y, then they are related. So this relation of being in the same subset has this property, and this property is called symmetry. But the relation is symmetric. If x is related to y, then y is related to x. Now, other relations you know about, for instance, greater than, one number being greater than another, that's clearly not symmetric. If x is greater than y, y is not greater than x. So not all relations are symmetric. And then the last property is transitivity. And that says that whenever you have a triple of elements, if x is related to y and y is related to z, that's the same way, those two statements, if they're both true, that implies that x must be related to z. This is called transitive. This, if you like, is saying that the relationship travels through intermediates. If x is related to y, and in turn, y is related to z, that means the relationship kind of travels through y, and it must be the case, it implies that x is related to z. That property is called transitivity, the relation being transitive. And an equivalence relation is a relation that satisfies all three properties. And we can appreciate by the relationship induced by partition satisfies that transitive property. I mean, if x and y are in the same subset, and there's another element that's in the same subset as y, well, and it has to be the same subset that the x was in originally. Okay, now that's very abstract, because we don't know anything about what this set is. It's just a set with elements in it, so it's not very meaningful at the moment. But this is a way of talking. It's a kind of set of terminology for simultaneously talking about splitting a big set up into subsets, and simultaneously talking about a relationship that holds amongst the elements of the subsets. And we will make a lot of use of it, and it'll become the key kind of viewpoint in chapter 6. But it's often regarded as a kind of a preliminary basic topic. But because you very early on you become familiar with the greater than equals, and equalities. So that's equivalence relations. And yeah, well, what are these theorems I thought we should look at? So 15, 20, and 25. So let's find those. Yeah, and then after relations, then he goes on and just introduces terminology to do with maps, functions. Functions from one set to another. When we're looking at groups, the chapters in homomorphisms and isomorphisms, these are these nice functions between groups. So as well as being interested in studying groups as sets with certain properties, we're interested in studying the relationship amongst universal groups, so to speak. And this relationships between groups is kind of carried by this notion of functions between groups, nice functions between groups. So the terminology of mapping, of having a domain and a codomain, of one-to-one and onto, we'll make a lot of use of that kind of stuff. So one-to-one and onto, remember, so how do you classify F in terms of injective and surjective there? Let's look at the answers. This function F, is it injective? No, why? No.
There's 2 and 3 both not to see.
Yeah. So this behavior of having more than one element mapped to the same element, that's not injective. That's 2-to-1. Okay. So the informal term for injectivity is 1-to-1. Yeah. So it's not injective. Is it surjective? No. Why?
It's nothing maps to A.
Nothing maps to A. Yeah. So a surjective function, when you declare that the function is from the set A to the set B, to be surjective, it must use up all of the elements of B. Every element of B must occur as an image of an element from the domain set. And so what about G? Well, then it does look surjective. If A, B, and C are the only things in B, then yeah, it is surjective. But again, it's not injective, because it's mapping 1 and 3 both to A. Ooh, but there's something, but yeah, there's something weird going on with G. Yeah, 1. So actually G, we shouldn't really call it a function. So I think that's the point he's making there. G is G, the relation F is about, yeah, so G we wouldn't regard, G is not a proper mapping or function. Because it's attempting to send 1 to 2 different destinations. So in our normal use of the terms function or mapping, that wouldn't qualify. That's not to say it wouldn't be it might still be mathematically meaningful to study this kind of a thing that associates 2 elements, A and B, to element 1, but it's not what we would term a mapping. So mapping our function for us here is going to be this process where you can take an argument and you get a unique value out from that argument. A single unique value. You don't get more than one value. So then these theorems then talk about operations between functions. The key important operation between functions for us is going to be composition. Find one function after another. So composition arises in this kind of situation where you've got a function f going from a set A to B, a function g going from a set B to C. Well, they're ripe for composing the two. Applying f first to A, and then immediately following it with the application of g to the values that you get out of f. That produces a function g after f. Remember, so if you got those two, you can glue them together in a way to get a function g after f will be a function sending A to C. And the way it works is, what is the value that this function takes at an element A? Simply g of f of A. Okay, that's the definition of composition of functions. When the functions line up, when the codomain of one function B is the same as the domain of another function G, then the two functions can be run together and composed in this way. So theorem 15 gives you certain facts about composition. First of all, it's an associative operation. You've got a third function h here, which could follow on. It goes from C to D. So h, g, and f could be composed in this order. First do f, then do g, then do h. But subtly, there's two different ways of actually carrying that out. You could first do h after g. Sorry, first do g after brain. First do G after H, and then do F after, then do that after F. Things are first, yeah. Or you could first apply G after F, and then afterwards apply H to it. It's a bit confusing because both of them just correspond. I mean, basically the proof of this is working out that both of those expressions, either side of the equal sign, when you apply them to an element A, you get H of G of F of A. First apply F, then apply G, then apply H. And it doesn't make a difference in kind of what pairwise order we specify the composition of. If F and G are both injective to begin with, then the composition will still be injective. So the composition preserves injectivity. Yeah. So remember, bijective means injective and surjective.
I feel like I should have been able to figure that out.
Yeah.
Yeah.
Injective and surjective. So composition maintains that property as well. If F and G are both bijective, then so is the composition. So theorems 1.20 and 125 are worth a look as well. Okay, so bijectivity is important. Being one-to-one and onto is important because that's exactly when the function has an inverse. The function has an inverse exactly when it's both one-to-one and onto. .125 is basically this picture here. 125 is this picture expressing the relationship between a partition and the relation that that induces on the elements, and saying that that's an equivalence relation. So it's just a very, here in 1.25 is just a very formal way of describing what I described here on this page. Okay. Doesn't mean a huge amount for us at the moment. But we'll see this tool or way of speaking being used in chapter 6 and all. So that's a very quick run through chapter 1. Which if you like are more or less attaching to maths fundamentals from the first year. Chapter 2 is attached to number theory from the second year. So we'll deal with this tomorrow. But we'll get a bit more active. I was mostly talking at you today. So tomorrow, the main important thing to take from this chapter, well, is basically the principle of induction, proof by induction, and the concept of divisibility and polynomials. We'll do a little bit of practice with that tomorrow, and then once we have that under our belts, we'll be all set to begin the study of proof theory as such with the lectures next week. Okay, so have a read through chapter. So that is a tomorrow night lecture. Yeah. So if you can have a look through chapter 1 tonight, maybe chapter 2 as well, and do some work with induction tomorrow. Okay.
Tomorrow's